Imagine you fall into a black hole, not all at once, slowly. You drift past the edge, the point of no return, and you keep going. In the movies, this is where you get crushed into nothing, but the math, when you do it carefully, does not say that. The math says something else. The math says you might come out the other side, not back where you started, somewhere new, a whole new universe, with its own stars, its own galaxies, its own night sky, and somebody, somewhere, looking up at it. Sounds like fiction until you turn it around. Because if every black hole leads to a new universe, then somewhere out there is a black hole that leads to ours. Somewhere out there, in a place we will never see, our universe is a black hole. And right now, in 2025, the deepest pictures ever taken of space are starting to whisper that this might be exactly what is going on. Make yourself comfortable, subscribe if you have not, and stick around, because tonight we're going to walk all the way down into this idea, gently, slowly, until you can see why so many physicists are starting to take it seriously. Let's dive in. Part 1. The question that stopped being rhetorical. There was a moment in late 2024, and then again in early 2025, when a sentence appeared in a great many people's feeds at roughly the same time. The sentence said, in one form or another, that the James Webb Space Telescope had found evidence that our entire universe might be inside a black hole. It was shared, and shared again, and shared again, and within a few days it had reached the kind of audience that, in earlier generations, only the announcement of a moon landing or the death of a famous person could reach. People who had not thought about cosmology in years stopped scrolling. People who had never thought about cosmology at all stopped scrolling. And then, after a day or two, the sentence moved on, the way these things do, and the world went back to whatever it had been doing. But the sentence was not exactly wrong. That is the strange part. If you traced it back, past the headlines, past the social media posts, past the breathless rewrites, what you found at the bottom of the chain was a peer-reviewed paper in the monthly notices of the Royal Astronomical Society. The paper was about galaxies, about spirals, about the direction in which they rotate. And the paper said something that, if you knew where to look, could be read as the first piece of observational support after 50 years of waiting for the idea that our cosmos is the inside of something larger. So the question got asked in passing, and then the question got put down, and then the question went away. But the question itself did not go away. The question is still sitting there. It is sitting there as you fall asleep tonight. And the strange part is, for the first time, the question is no longer rhetorical. Tonight, we're going to take it down off the shelf. We're going to walk through it slowly. We're going to look at the paper, and the paper behind the paper, and the half-century of mathematics behind the paper behind the paper. We're going to look at 4 separate observations, each of which is small, each of which is contestable, each of which by itself is the kind of mild puzzle that often dissolves on closer examination. And then we're going to put them side by side and ask what shape they make together. The shape they make together is not by itself a proof. I want to be clear about that from the beginning. There is no announcement we're about to play for you. There is no professor on a stage saying we have figured it out. There is instead a very particular kind of cosmic tension. The tension you feel when several independent pieces of information, each one individually weak, all start to point in the same direction. The tension of a pattern that refuses to disperse. Most nights, when this channel takes on a question this large, the question turns out to be a story about ourselves, about what we are willing to believe, about how much weight we can hold before we set it down, about what changes inside us when we look out at the sky and notice that the sky is not behaving the way the textbook said it would. Tonight is one of those nights. The cosmos that you have been living inside for your whole life may be a slightly different cosmos than the one you thought it was. The matter you're made of may have a history that is older and stranger and more enclosed than any of us were taught. We're going to take this carefully. We are not going to overstate. We are not going to make the claim larger than the data supports. We are going to follow the actual numbers, the actual papers, the actual physicists, and the actual mathematics. We are also going to follow the strange, quiet feeling that builds when you realise that a question you have asked your whole life, sometimes seriously and sometimes as a joke, has begun to acquire an answer. Because that is the truth at the bottom of this. The question is no longer rhetorical. People are working on it. Telescopes are being pointed at it. Numbers are being calculated. And within the next 10 years, almost certainly we will know. Let us start where the moment started. With a single image sent home from a telescope 1,000,000 miles from Earth, and what someone saw when they sat down and counted what was in it. But before we get there, I want to plant a phrase that we will come back to several times tonight. A phrase that, by the end, will mean something different than it means right now. The phrase is this: we are inside something. I want you to hold those 4 words gently. We will return to them. We will turn them over. By the end of the night, we will know what they mean. Now let us walk into the picture. In April 2023, and again in December 2023, and again in 2024 and into 2025, the James Webb Space Telescope released a series of deep field images from a survey called JDS. The full name is the JWST Advanced Deep Extragalactic Survey, and the purpose is exactly what the name implies. JDS is meant to look as far back in cosmic time as Webb's instruments can reach, and to catalogue as many galaxies as possible at those depths. The numbers involved are dizzying. JDS has resolved tens of thousands of galaxies across a tiny patch of sky, many of them from the first billion years after the Big Bang, some of them from epochs so early that the universe was only a few 100 million years old. When the JDS images began to circulate, most of the scientific attention went toward the obvious questions. How early did galaxies form? How rapidly did they grow? Why are some of them already so massive when the standard model says they should still be young and small? Those questions are real, and they have driven many of the other videos we have done this year. The little red dots problem, the high redshift maturity puzzle, the Hubble tension at the upper end of the distance ladder, each of those is its own deep dive. But while everyone else was looking at the brightnesses and the masses and the spectra, one researcher was looking at something else. He was looking at the shapes, specifically at which way each spiral galaxy was spinning, and what he found when he counted them all was something he had been quietly expecting for almost a decade, and that the standard model of cosmology had been quietly insisting could not be there. The researcher's name is Lior Shamir. He is at Kansas State University. His background is unusual for this kind of work. He is by training a computer scientist, with a long history of building algorithms that classify astronomical images at scale. He spent the 2010s building tools that could look at Sloan Digital Sky Survey images and Pan-STARRS images and assign each galaxy a rotation direction, automatically, by analysing the curvature of the visible spiral arms. He did this on samples of tens of thousands of galaxies, and he kept finding again and again that the rotation directions were not coming out evenly split. In an isotropic Big Bang cosmology, the universe at large scales has no preferred direction. Every part of it should look statistically the same as every other part. Galaxies should form from gas clouds whose rotation directions are random. When you survey enough of them, the count should converge on 50% rotating one way and 50% rotating the other. The exact split on any finite sample will of course bounce around a little. That is what statistical fluctuation looks like. But on tens of thousands of galaxies the bounce should be small. It should sit at 1 or 2% above or below the 50-50 line, not more. Shamir kept finding more. In the Sloan data, the asymmetry was small but consistent. In Pan-STARRS, the asymmetry was small but consistent. He published the results. The papers passed peer review. The mainstream community largely set them aside. The argument was that the asymmetry, if it was real, was probably an artifact of the imaging telescopes themselves, or of the classification algorithm, or of some subtle selection effect in which galaxies got reliably resolved at which angles. There were specific technical reasons to be sceptical, and Shamir worked carefully through each one over the course of multiple follow-up papers. Then JWST came online, the JADES data became available, and Shamir asked the same question on the new data set. The same question, the same procedure. He took 263 spiral galaxies whose arms were clearly resolved in the JADES images. He classified each one for rotation direction. He counted. 158 rotated in one direction. 105 rotated in the other. That is, mathematically, 60% versus 40%. In a sample of 263, that is well outside the range of normal statistical fluctuation. The chance probability of seeing such a split, if the underlying distribution were truly 50-50, is small enough that, if you were rolling dice, you would notice. You would notice quickly. You would suspect the dice were weighted. The result was published in March 2025. The paper appeared in the monthly notices of the Royal Astronomical Society. That journal is one of the oldest and most respected astronomy journals in the world. The paper is not a preprint floating on the internet. It is not a press release. It is a refereed scientific publication in a journal whose editors and reviewers have been doing this for a long time. The asymmetry, in other words, has been examined by other professionals, and it has been allowed to enter the scientific record. This does not mean the interpretation is settled. We will get to the interpretation. What it means is that the measurement is real. The number is real. The sample is real. The 2/3 versus 1/3 split is the actual content of the actual paper, and the paper has actually been peer-reviewed and actually been published. Everything that comes next in this video is downstream of that fact. So let us hold that fact for a moment, while we step back, because the natural next question is one most people will ask without thinking. 263 is a small number. There are billions of galaxies out there. Could this just be that we happen to point Webb at a slightly weird patch of sky? The answer, and this is the part Shamir has been building toward for nearly a decade, is no. Because the same asymmetry, in the same direction, of roughly the same magnitude, has been showing up at every redshift range and on every instrument he has applied his algorithm to. Low redshift, high redshift, Sloan, Pan-STARRS, Webb. They all bend the same way. If the asymmetry were a feature of the small patch of sky Webb happens to be looking at, it would not appear in the much larger Sloan samples drawn from the rest of the sky. It does. If the asymmetry were a feature of one instrument's optics, it would not survive when the data is taken with completely different telescopes and completely different detectors. It does. If the asymmetry were a feature of how the classification algorithm interpreted the images, it would not survive when independent human observers, blinded to the algorithm's result, classified the same galaxies. Shamir has done that test. The asymmetry survives. If the asymmetry is real, then the universe at large scales has a preferred direction. And a universe with a preferred direction is not the universe that the standard inflationary Big Bang model predicts. Either the standard model is incomplete, or the universe inherited a preferred direction from somewhere, from something, from outside. Hold that thought. We will come back to it. Tonight, we're going to walk through every piece of this slowly. What a rotating universe means in the equations, where the idea that the universe might be inside a black hole actually comes from, how old the idea is, the other observations that bend in the same direction, and what comes next. But first, let us settle into what Shamir actually saw, because the small room where the counting happened is one of those moments in science where a person sits in front of an image and notices something the universe was not supposed to say, and those moments are worth slowing down for. Part 2. Counting Galaxies in a Quiet Room. It is late in the evening, and somewhere in Manhattan, Kansas, there is a workstation with 2 large monitors and a coffee that has gone cold an hour ago. The room is quiet. Outside the window, the campus is dark. The building's heating system makes a faint, regular sound, on and then off and then on again, the way these buildings do. The light in the room comes from the monitors. On the left monitor is a spreadsheet. On the right monitor is an image from JWST. The image is enormous, even at the resolution the screen can display. There are galaxies everywhere. Foreground spirals, background ellipticals, tiny smudges that are entire galaxies, billions of years old, billions of light years away. Leo Shamir is sitting in front of the monitors. He's looking at one galaxy at a time. He's identifying the direction of its arms. He's marking it. He's moving on. I want you to put yourself in that room, not as a metaphor, literally. Sit in the chair. The cursor on the screen blinks. The image is so deep that there are galaxies behind galaxies behind galaxies. You can pick a single point in the image, somewhere in the middle, and zoom in, and what was a featureless dot becomes a spiral, and the spiral has arms, and the arms curve in one direction. You write it down. You move the cursor. The next galaxy. Different shape. Arms curve in the opposite direction. You write it down. The next galaxy. You move slowly. Each image takes a few seconds to interpret. Sometimes it takes longer because the galaxy is at an angle, or partially occluded, or simply too faint at the edges to read with confidence. The borderline ones get set aside. Only the ones you can read with certainty get counted. After the first 50 galaxies, you have a tally. It is roughly 35 going one way and 15 going the other. You note it. You keep going. This is not unusual for a small sample. Statistical fluctuation can produce that kind of split in 50 trials without anything strange being true. By the time you reach 100 galaxies, the split is roughly 60 going one way and 40 going the other. Still possible by chance, but starting to feel a little tilted. You keep going. The night gets later. The coffee gets colder. The number keeps climbing. By the time you reach 200 galaxies, you have 120 going one way and 80 going the other. That is 60 to 40. At this point, the math has started to murmur. You know what the standard model says. You know what the inflationary Big Bang predicts. You know that at this sample size, a 60-40 split should have rolled itself back toward 50-50 by now. It has not. It is sticking. You keep going. 263 galaxies. Final count, 158 clockwise, 105 counterclockwise. You sit back in the chair, you look at the number. The light on the monitor is the only light in the room. The coffee is cold. The campus is dark. You've been doing this for 10 years, ever since you first noticed the asymmetry in the Sloan data. You have published the papers. You have run the cross-checks. You have answered the technical objections. You have heard, over and over, that the result must be an artifact of the imaging, an artifact of the algorithm, an artifact of the small samples. And now you have Webb. Now you have the deepest data set in the history of optical astronomy, and the number on your screen says the same thing the Sloan data said, and the Pan-STARRS data said, and every data set you have ever applied this procedure to has said. The universe is rotating, or, and this is the part that even Shamir is careful about, the universe at the scale we can see is exhibiting a coherent net angular momentum that should not be there if the Big Bang was perfectly isotropic and inflation perfectly smoothed all anisotropies. The data does not speak in plain English. The data says only what it says. The interpretation is a separate step, but the count is in. It does not balance. You log off. You close the spreadsheet. You go home. The next day, you start writing. The paper takes months. There are checks to run. There are statistical robustness analyses. There are independent verifications. You take the same JD's images and you randomly mirror them. Flip them along an axis so that clockwise galaxies become counterclockwise galaxies and vice versa. And you run your algorithm on the mirrored images. If your algorithm has a built-in preference, that preference will produce the same asymmetry on the mirrored images as on the originals. It does not. The mirrored images produce the opposite asymmetry, exactly as the input dictates. This rules out the algorithm bias objection. You ask human classifiers, blinded to the algorithm's result, to classify the same galaxies independently. They produce roughly the same split. This rules out the algorithm as only source objection. You compare the asymmetry to the orientation of the Milky Way's own rotation axis to check whether you might be seeing a local effect. The asymmetry persists when the Milky Way's orientation is rotated out of the data. This rules out the local geometry objection. You compare the result to similar analyses by other authors using different methods. The asymmetry is real, in the sense that more than one investigator, using more than one method, has now detected it. Magnitude and direction are consistent across studies. The paper is submitted. The reviewers ask questions. The questions get answered. The paper is accepted. The monthly notices of the Royal Astronomical Society publishes it in March 2025. The press release goes out. The coverage begins. This is the moment when the public story diverges from the scientific story, and the divergence is worth pausing on. In the public version, JWST has found evidence that we live inside a black hole. That is not strictly what the paper says. What the paper says is that the rotation directions of spiral galaxies in the JD sample are asymmetric at a statistically significant level, and that this asymmetry is consistent with several theoretical frameworks that predict a universe with a preferred axis, including but not limited to the framework in which the universe is the interior of a rotating black hole. The paper is careful. The paper is technical. The paper does not by itself prove anything about black holes. But the implication, once you start chasing it through the equations, is unavoidable. Because if the universe has a preferred axis, then either inflation is wrong or incomplete, or the initial conditions of the universe were not what we thought they were, or the universe inherited an axis from somewhere larger than itself. Those are the three options. There is no fourth option that preserves the standard isotropic Big Bang as stated. This is why the result mattered. Not because Shamir announced anything, not because anyone declared a conclusion, but because the data, sitting on the workstation in the quiet room in Kansas, had stopped agreeing with what every introductory cosmology textbook in the world says about the universe at large scales. 2/3 versus 1/3. The mass of the universe, when you arrange it into galaxies and let those galaxies spin, prefers a direction. The universe is inside something, or it remembers being inside something, or it has an axis for some other reason that the standard model has not anticipated. We are still in the foothills of this story. We have not yet gotten to the mathematics that lets you ask whether the cosmic horizon is also an event horizon. We have not yet gotten to the 50-year-old paper that quietly predicted exactly this measurement. We have not yet gotten to the bounce, or the parent universe, or what it means to fall into Sagittarius A. We are still standing in the doorway. The doorway is the data. The data is the count. But you should know, before we go further, that the count is not in dispute. Critics of the universe inside a black hole picture have written long responses to Shamir's paper, suggesting alternative interpretations, primordial vorticity, subtle selection effects, unmodelled systematics. The case is ongoing. What they have not argued is that the count is wrong. The 263 galaxies, the 158 clockwise, the 105 counterclockwise, those numbers are not contested. What is contested is what they mean. That is where we are. The number is real. The interpretation is open. The next decade of telescopes will decide. We have time. Let us use it. Let us walk through what an axis would mean, and where the idea that the universe could be inside a black hole comes from, and why this measurement is the first thing in 50 years that has given that idea a piece of observational ground to stand on. But before we move, let us return to the room, the workstation, the cold coffee, the quiet hum of the building, the screen with the spiral galaxies, the cursor blinking, the person in the chair having just counted the universe and found that the universe prefers a direction. They will get up, eventually. They will turn off the monitor. They will go home. The galaxies will keep rotating in the directions they have been rotating in for billions of years, indifferent to whether anyone has counted them. The data sits on the disk. The paper is being written. The count is in. We're inside something. Hold those 4 words. We will return to them. For now, we step out of the room and into the math. Part 3. What a rotating universe would mean. To understand why 2/3 versus 1/3 is, in the language of cosmology, a small earthquake, you have to understand what the standard inflationary Big Bang model actually predicts about the rotation directions of galaxies at very large scales. The prediction is simple, the prediction is also very strong, and it is the strength of the prediction, more than the magnitude of the asymmetry, that makes the Shamir result interesting. The standard model goes like this. In the first tiny fraction of a second after the Big Bang, somewhere around 10 to the negative 35th seconds in, the universe underwent a brief epoch of exponential expansion called inflation. Inflation was first proposed by Alan Guth in 1980, and refined by Andre Linde and Paul Steinhardt and others over the following years, and it has become the standard explanation for several otherwise inexplicable features of the universe we observe. Inflation explains why the cosmic microwave background is so uniform. Uniform in temperature to roughly 1 part in 100,000 across the entire sky, even between regions that, in a non-inflationary cosmology, would never have been in causal contact with one another. The smoothness of the cosmic microwave background was, before inflation was proposed, one of the great mysteries of cosmology. Inflation solves it by saying those distant regions were in causal contact, before inflation stretched them apart faster than light could keep up. Inflation also explains why the universe is geometrically flat at the precision we can measure. A universe that began curved would, in the standard Friedmann equations, evolve away from flatness over time. Inflation flattens the geometry to such an extreme degree that any initial curvature is washed out and unobservable from inside our cosmic horizon. And inflation also explains, or is supposed to explain, why the universe at large scales has no preferred direction. If you start with any initial anisotropy, any axis, any rotation, any preferred direction at all, inflation, by stretching the universe by a factor of roughly 10 to the 26th or larger over a span of fewer than 10 to the negative 33rd seconds, would dilute that anisotropy by the same enormous factor. Whatever rotation the pre-inflationary universe had, the post-inflationary universe would have effectively none. The rotation would survive only at the unobservable level of 10 to the negative 20-something radians per Hubble time. It would not show up in surveys of galaxy rotation. It would not show up in CMB anisotropy measurements. It would not show up in anything we can see. That is the prediction. Inflation says the universe should be smooth, flat, and rotationally featureless at large scales. The cosmic microwave background, when Planck mapped it in 2013 and 2018, was indeed extraordinarily smooth. Inflation passed the smoothness test. The universe is indeed extraordinarily flat. Inflation passed the flatness test. And until Shamir's analyses started accumulating, the universe also appeared to be rotationally featureless at large scales. The standard galaxy surveys had not detected a preferred rotation axis. The hypothesis seemed clean. What Shamir's result suggests is that the universe is not rotationally featureless. It is instead slightly but persistently asymmetric in galaxy rotation direction at every redshift we have measured. This puts the standard inflationary model in an awkward position. Either inflation did not happen as described, in which case the smoothness and flatness need different explanations, or inflation happened but did not fully dilute the initial anisotropy, in which case the inflationary epoch was substantially shorter than the standard 60+ E-foldings most models assume. Or inflation happened and did fully dilute the initial anisotropy, but the universe acquired a new anisotropy after inflation, from some mechanism we have not yet identified. The third option is the one black hole cosmology lives in, because black hole cosmology says the universe inherited its anisotropy from the geometry of the parent universe black hole inside which our universe formed. The inheritance is not pre-inflationary, it is structural. It is built into the geometry of the space-time we live in, and it does not dilute under expansion because it is a property of the boundary, not of the interior contents. If you're not used to thinking about geometry this way, here is the intuition. Imagine you're a fish in an aquarium. The aquarium is rotating slowly. You, the fish, do not directly feel the rotation, because the water moves with the glass and the glass moves with the rotation. But the rotation leaves a signature in the way water at different depths flows, in the way debris settles, in the way patterns develop over time inside the tank. The fish, if it is a careful observer, can deduce the rotation of the tank by measuring the way things inside the tank move with respect to one another. The fish never directly sees the outside of the tank, but the rotation is there. The tank carries it. The water carries it. The fish, slowly, picks it up. That is the picture. The universe is the tank. We are the fish. The Big Bang did not produce the rotation. The geometry of the cosmic container produced the rotation. The rotation is inherited. The rotation is structural. This is not the only possible explanation for the Shamir result. We will come to the alternatives. But it is, by some distance, the cleanest explanation. It is the one that predicts the rotation asymmetry from first principles. It is the one that does not require inflation to be modified, or initial conditions to be fine-tuned, or unknown mechanisms to be invoked. It is, in the language of physicists, the most natural explanation. There is another way to see why this matters, and it has to do with the way angular momentum behaves in physics. Angular momentum is conserved. Once a system has it, that angular momentum does not vanish. It can be transferred, distributed, hidden in subsystems and recovered later. But the total does not change unless an external torque is applied. If the universe has angular momentum at large scales today, then either it had that angular momentum throughout its history, in which case it had to start with it, or the universe acquired it from outside by some kind of external torque. The first option requires the initial conditions to include angular momentum. The second requires there to be an outside for it to come from. Inflation, in the standard picture, begins with a quantum vacuum fluctuation. Those fluctuations are not supposed to have a net angular momentum. They average to zero. Any individual realization can have small fluctuations, but they should be small. 2/3 versus 1/3 is not small. It implies that the initial conditions of the universe had a net angular momentum that survived inflation. Either inflation was less efficient at smoothing than the standard model assumes, or the angular momentum was so large to begin with that even 60+ e-foldings could not erase it. Both options point in the same direction. They point at a universe whose origin was inside something that already had angular momentum to transfer, a parent system, a larger geometry, something the universe was born from and inherited from. This is where the black hole picture starts to look not just consistent with the data, but actively explanatory. The black hole picture says, of course the universe has angular momentum. Of course it has a preferred axis. Of course it is rotating. The Kerr black hole inside which it formed has angular momentum, has a preferred axis, is rotating. The universe is the interior of that Kerr black hole. The inheritance is structural. The asymmetry is a fingerprint of the parent geometry. And here is the part that, when you sit with it, becomes hard to set aside. The Schwarzschild metric describes a non-rotating black hole. The Kerr metric, derived by Roy Kerr in 1963, describes a rotating black hole. A non-rotating black hole has a spherical event horizon. A rotating black hole has a more complex horizon structure, including an ergosphere, a region outside the event horizon where the rotation of the black hole drags space-time along with it in a way that no inertial observer can resist. If the universe is the interior of a Kerr black hole, then the universe is sitting inside the rotation of a Kerr metric. The rotation of the parent black hole would, by the natural geometric consistency of the Kerr solution, induce a rotation in the interior space-time as well. The interior would have a preferred axis. The interior would have a net angular momentum. Galaxies forming inside would statistically have rotation directions correlated with the parent black hole's spin axis. 2/3 clockwise, 1/3 counterclockwise. That is what you would predict, from the geometry alone, without any other input. This is why Shamir's result, while small in absolute terms, lands with the weight that it does. Not because 263 galaxies is a large sample. It is not. Not because the asymmetry is enormous. It is not. But because the asymmetry is in the direction the black hole interior picture predicts, with roughly the magnitude the black hole interior picture predicts, surviving cross-checks that should have eliminated it if it were spurious. It is the kind of result that, if you had asked Pathria in 1972 what observation would, in his lifetime, give his hypothesis its first piece of observational support, he might well have described something close to this. He did not live to see it. Raj Pathria died in 2014. The first observational hint that his 1972 paper had been onto something arrived in 2025, a decade after his death, in a journal he had published in himself. That is the way these stories go sometimes. The idea is planted. It sits, watched only by a handful of physicists who refuse to let it die. The decades roll past. Telescopes get built. Surveys get run. And then, one quiet evening in Kansas, a count comes in, and a phrase from a paper most people stopped reading decades ago suddenly applies again. The universe is the interior of a black hole. That is what Pathria said. That is what the count says, gently, in the language of a sample too small to declare anything, and too consistent to dismiss anything. We're still walking down into this. The numbers will get larger, the implications will get stranger, but the foundation is what we just walked through. The standard inflationary Big Bang model predicts no preferred direction. The data, in 2025, suggests there is one. The simplest explanation for there to be one is that the universe inherited it from a parent geometry. The simplest parent geometry that produces this kind of inheritance is a Kerr black hole. Therefore, the universe may be the interior of a Kerr black hole. Each step is small. None of the steps is forced, but each step is the most natural option in the absence of stronger evidence for an alternative. Let us walk down to the next step. Let us walk down to 1972 when this was first written down in a paper that did not get the attention it should have by a man whose name most listeners will not have heard. Part 4. The paper that sat for 50 years. In 1972, a physicist named Raj Pathria published a short note in Nature. The note was titled simply, "The Universe as a Black Hole." It ran a few pages. It did not generate much excitement at the time. It was not on the front of the journal. It was not the subject of any conference talk. It was, in the language of academic publishing, a curiosity, a thought experiment, a clever calculation by a respected physicist who, the year before, had been mostly known for his work on statistical mechanics. The note proposed that the observable universe, taken as a whole, could be interpreted as the interior of a Schwarzschild black hole embedded in a larger Einstein universe. That same year, almost simultaneously, the British mathematician and statistician I.J. Good, better known to history as the codebreaker who worked with Alan Turing at Bletchley Park, and as one of the architects of the early theory of artificial intelligence, published an independent note in Physics Today proposing essentially the same idea. The two papers were not aware of each other while being written. They reached the same conclusion by different routes. They both said the same thing. The mass of the observable universe, divided by the volume of the observable universe, gives an average density. The Schwarzschild formula tells you, given a mass, what the radius of the corresponding black hole would be. Run the calculation. The radius comes out close to the radius of the cosmic horizon. Therefore, the universe satisfies the equation that defines a black hole at its own scale. I want to make this concrete, because the calculation is short and the answer it gives is one of the strangest single numerical facts in physics, and you can carry it with you for the rest of your life if you understand what it means. The Schwarzschild radius of a black hole is given by the formula R equals 2gm over c squared. G is Newton's gravitational constant. M is the mass of the black hole. C is the speed of light. The formula is linear in mass. twice as much mass, twice as large a Schwarzschild radius, 10 times as much mass, 10 times as large a Schwarzschild radius. The relationship is clean. Now plug in numbers. The mass of the observable universe, including all the ordinary matter, all the dark matter, all the energy that contributes to the gravitational field at cosmological scales, is approximately 10 to the 53rd kilograms when you count only ordinary matter, and approximately 10 to the 54th kilograms when you include dark matter and the energy contributions of dark energy. Plug 10 to the 54th into the Schwarzschild formula, multiply by 2g, divide by c squared, the numbers grind through. The answer comes out at approximately 15 billion light-years. The radius of our observable universe, the distance to the cosmic horizon, the boundary beyond which light has not had time to reach us in the age of the universe so far, is approximately 14 billion light-years. 15 and 14, within order unity, within the error bars of every measurement that feeds into either calculation. The mass and the radius of the universe satisfy the Schwarzschild equation. To within the precision of cosmology itself. This is the coincidence Pathria pointed out. This is the coincidence Good pointed out. This is the coincidence that has, for 50 years, refused to go away. You can imagine when these two papers came out in 1972, the conversation they might have started. They did not. The mainstream of cosmology in 1972 was still settling into the standard Big Bang model. The cosmic microwave background had been discovered only 7 years earlier. The basic Friedmann equations were still being absorbed by graduate students and applied to observational cosmology in serious ways. The idea that the universe might, in any meaningful sense, be the inside of a black hole was treated as a numerical curiosity, possibly a coincidence, possibly meaningless, probably worth noting once and setting aside. Pathria and Good did note it. They did set it aside. They went on to other work. Pathria continued his career in statistical mechanics. Good continued his work on Bayesian probability and artificial intelligence. The papers sat. In 1994, a physicist named Mark Stuckey at Elizabethtown College in Pennsylvania picked the idea back up. He wrote a paper in the American Journal of Physics that derived, with more rigour than Pathria or Good had used, the conditions under which the interior of a black hole could correspond to a Friedmann-Robertson-Walker cosmology, the standard mathematical framework of the Big Bang. Stuckey showed that the mapping was consistent. The interior of a Schwarzschild black hole, under appropriate boundary conditions, could be reinterpreted as a closed Friedmann universe. The mathematical equivalence was tighter than people had supposed. Stuckey also reran the coincidence calculation with updated values for the cosmological parameters. The calculation still worked. The numbers had been revised upwards several times since 1972. Dark matter had been added to the inventory of cosmic mass, and the implications for the total were significant, and the coincidence had survived every revision. The radius of the universe's Schwarzschild equivalent still matched the radius of the observable universe, to within order unity. In 2001, Damien Eason and Robert Brandenberger wrote a paper in the Journal of High Energy Physics that took the idea further. They asked, if the universe were the interior of a black hole, what would have happened at the origin? Could the interior have begun from a non-singular bounce inside the parent black hole, rather than from a singular Big Bang? They showed that, in certain parameter regimes, the answer was yes. The Big Bang in this picture was not the beginning. The Big Bang was the rebound. Then, starting in 2010, a physicist named Nikodem Popławski at Indiana University, and later at the University of New Haven, began publishing a series of papers in Physics Letters B and other journals. Popławski's approach was different. He took the Einstein-Cartan extension of general relativity, which includes a term for the spin-angular momentum of fermionic matter, a term that is normally negligible but becomes important at extreme densities, and applied it to the cosmological case. What he found was that the spin-angular momentum of fermions, at densities above approximately 10 to the 54th kilograms per cubic meter, produces a repulsive torsion. The torsion is, in standard general relativity, set to 0. In Einstein-Cartan-Kibble-Siyama theory, it is not. When matter collapses inside a black hole, in Popławski's picture, it does not become a singularity. The Fermion spin torsion repels the collapse before infinite density is reached. The matter rebounds. The rebound is mathematically indistinguishable from an inflationary expansion. The expansion proceeds. The interior of the black hole becomes a new universe. The new universe inherits the angular momentum of the parent black hole, distributed through the rebound, and shows up at large scales as a preferred axis. This is the picture that, in 2025, the Shamir result has begun to support. Not directly, not conclusively, but consistently. The line from Pathria's 1972 paper to Popławski's 2010 papers to the Shamir 2025 result is a thread. The thread runs through Good, through Stuckey, through Eson and Brandenberger, through other authors we have not named, Bertolami, Brassard, several others, who quietly developed the picture across half a century. Each contributor added a piece. Pathria and Good added the original coincidence. Stuckey added the mathematical equivalence with closed Friedmann cosmologies. Eson and Brandenberger added the bounce. Popławski added the torsion mechanism for the bounce. And Shamir in 2025 added the first observational signature that distinguishes this picture from the standard model. It is a thread that has survived because the people working on it could see, at each step, that the pieces fit together. The Schwarzschild coincidence has not disappeared. The mathematical equivalence has not been refuted. The bounce mechanism has not been ruled out. The torsion physics is consistent with all current observations, and now the rotation asymmetry is sitting on the data. Each piece is small, the pattern is not. What is striking, looking back across the 50 years, is how patient the picture has been. There have been no press releases, no dramatic announcements, no conferences declaring victory. The picture has instead accumulated. It has built up piece by piece. The contributors have, by and large, been physicists known for other work, who took an interest in the question and added what they could and moved on. It is the kind of slow, patient accumulation that is sometimes how the largest changes in physics happen, not in a single burst, in a 50-year drift. That drift is now, for the first time, intersecting with new data, not Sloan Digital Sky Survey data, not Pan-STARRS data, Webb data, the deepest images of the early universe humanity has ever taken. And the count when Shamir ran it came up 2/3 to 1/3. This is the moment where, if the picture is going to make its case, it has to make it in the open. The data is there, the community is watching, the papers are coming in. 2025 was the year the question opened. The next decade will be the years the question closes. Now we have to ask, what does the actual mathematics of the Schwarzschild coincidence say? Not in summary, in detail, because the strangeness of the picture is in the numbers, and the numbers are worth sitting with. Let us go to the calculation. But before we do, hold the phrase one more time. We are inside something. The Pathria paper said it with mathematics. Good said it with a paragraph in Physics Today. Stuckey said it with a metric. Popławski said it with a torsion tensor. Shamir said it with a count of 263 galaxies. Each one of them was saying, in their own language, the same thing. We're inside something. The thing has a shape. The shape has consequences. The consequences are starting to show. Now to the math. Part 5. The coincidence that will not go away. Let us take the calculation slowly. The numbers are not difficult. The difficulty is what they suggest, and the strangeness of what they suggest is, in a real sense, the load-bearing argument that everything else in this video rests on. The Schwarzschild radius formula was derived by Carl Schwarzschild in 1916, less than a year after Albert Einstein published the field equations of general relativity. Schwarzschild was a German physicist serving on the Eastern Front during the First World War. He worked the equations on the battlefield, in between his actual duties as an artillery officer. He sent the solution to Einstein in a letter. Einstein read it in the morning and replied immediately. The solution was, Einstein said, more compact and more elegant than he had thought possible. Schwarzschild did not live to see his solution become famous. He died a few months later of a skin disease contracted at the front. The formula he sent to Einstein in that letter is the formula we have been using, r equals 2gm over c squared, the radius of the event horizon as a function of the mass within. The formula is linear, twice the mass, twice the radius, 10 times the mass, 10 times the radius. The relationship is exact in the Schwarzschild solution. It is the defining geometry of a non-rotating black hole. Now apply the formula at the cosmological scale. The mass of the observable universe is a number you can estimate several different ways, and the estimates converge. You can take the average density of matter and energy in the universe, which has been measured by Planck and other CMB experiments to be approximately 10 to the negative 27th kilograms per cubic meter, and multiply it by the volume of the observable universe, which is approximately 10 to the 80th cubic meters. The result is approximately 10 to the 53rd kilograms. That is ordinary matter. If you include dark matter, which most cosmologists agree must be there to explain galaxy rotation curves and large-scale structure formation, the mass goes up by a factor of about 6. So ordinary matter plus dark matter together comes to approximately 6 times 10 to the 53rd, or roughly 10 to the 54th kilograms. If you also include the energy contribution of dark energy, which acts gravitationally even though it is repulsive in the late universe, the total comes out at roughly the same order of magnitude, give or take a factor. So, roughly 10 to the 54th kilograms, that is the mass of the observable universe, total. Now plug it into the Schwarzschild formula. Multiply by 2g. G is 6.67 times 10 to the negative 11 in standard units. So 2gm is approximately 1.3 times 10 to the 44th in meters per kilogram squared times kilograms, which simplifies to meters. Divide by c squared. C is 3 times 10 to the 8th meters per second. C squared is 9 times 10 to the 16th meters squared per second squared. Divide. 1.3 times 10 to the 44th divided by 9 times 10 to the 16th comes out at approximately 1.4 times 10 to the 27th meters. 1.4 times 10 to the 27th meters. The radius of the observable universe is approximately 14 billion light-years. A light-year is approximately 9.5 times 10 to the 15th meters, so 14 billion light-years is approximately 1.3 times 10 to the 26th meters. The Schwarzschild radius of a black hole with the mass of the observable universe is approximately 10 times larger than the observable universe. If you use only ordinary matter, 10 to the 53rd kilograms instead of 10 to the 54th, the Schwarzschild radius drops by a factor of 10 to approximately 1.4 times 10 to the 26th meters, which is the radius of the observable universe. If you use intermediate values, counting some but not all of the dark matter, or including only the matter inside a specific causal horizon, rather than the full observable universe, the numbers swing back and forth across the same range. But the answer always comes out within a factor of order unity. Within the error bars, the match is robust to the choices you make about which mass to count and which horizon to use. This is the Schwarzschild coincidence. It is, in plain terms, the observation that if you took all the mass we can see and asked what size black hole that mass would form, the answer is a black hole roughly the size of our visible universe. You can imagine a few possible reactions to this. The first is to dismiss it as numerical accident. The trouble with the dismissal is that it has not survived testing. The numbers have been revised many times. Dark matter was added. The coincidence held. Dark energy was added. The coincidence held. The Hubble constant has been revised. The coincidence held. WMAP, Planck, now CMBS4 preliminary data, the coincidence has held. If it were a one-time accident, it should have broken by now. It has not. The second possible reaction is to say that the coincidence reflects something deep about cosmology that we do not yet understand, but does not necessarily mean the universe is inside a black hole. Several cosmologists have argued that the cosmic horizon happens to coincide with the Schwarzschild radius of the universe's mass at the current epoch as a consequence of expanding universe geometry. The trouble with this interpretation is that it does not by itself explain why. It restates the coincidence in different language. The third possible reaction is to take the coincidence at face value, to say, the mass of the observable universe satisfies the equation that defines an event horizon. That equation is the Schwarzschild equation. Therefore, the universe, at the scale we can see, sits inside an event horizon defined by its own mass. Therefore, we are, in the most literal sense the mathematics permits, inside a black hole. I want to pause on that phrase because it is going to come back later, and I want to make sure we have heard it once carefully. The mass of the universe satisfies the equation that defines an event horizon. That is what the calculation says, not as a metaphor, as an equation. The phrase is, in a different sense, a way of describing the situation that does not require any unusual physics. The Schwarzschild equation is a perfectly ordinary equation. The mass of the universe is a perfectly ordinary quantity. The fact that they satisfy the equation is, in one sense, just a number coming out to a particular value. But in another sense, it is the kind of number that, when it appears, has historically meant something. Newton's inverse square law in the gravity of the solar system was, before Newton, just a numerical fit between the orbits of the planets. The fit turned out to be a law. The fact that planetary orbits matched an equation was not an accident. It was the equation describing the actual physics. It is possible the Schwarzschild coincidence is, in the same way, the equation describing the actual physics. That the universe is satisfying the Schwarzschild equation not because of a random accident, but because the universe is, at its scale, what the Schwarzschild equation describes, a black hole. This is the interpretation Pathria and Good chose in 1972. Stuckey refined it in 1994. Eason and Brandenburger built on it in 2001. Popławski supplied a mechanism for it in 2010. And in 2025, the Shamir result has supplied the first piece of observational support for it that distinguishes it from the standard isotropic Big Bang. The coincidence will not go away. The interpretation, increasingly, is being taken seriously by people who have spent their careers in cosmology and who are not given to wild speculation. The frame within which we live appears, to the precision we can measure, to be defined by an equation we usually associate with collapsed stellar remnants and the centres of galaxies. The frame is a black hole. We're inside it. The math says it, quietly, repeatedly, for 50 years in increasingly polished derivations, and here, with the calculation freshly in mind, is a thing worth pausing on. We just went through a calculation that involved the mass of the universe, the actual matter content, hydrogen atoms, helium atoms, carbon, oxygen, iron, the atoms in your body, the atoms in this room, the atoms in the food you ate today. They all factor into that 10 to the 54th kilograms. The calculation we just ran was not abstract. It included you. The Schwarzschild equation, applied to the universe, was applied to a sum of matter that includes the carbon in your fingertips and the iron in your blood. When the equation comes out matched to the horizon, it is your matter that satisfies it. Hold that. It is, in a way, the first emotional weight of this video. The math is not happening at us. The math is happening through us. We are part of the count. Now, with the math in hand, let us look at the mechanism. Pathria and Good showed the coincidence. They did not show how a universe could get inside a black hole. Popławski did. We're going to walk through Popławski's bounce next, and we're going to put you, gently, inside the matter that did the bouncing. Part 6. The bounce. Nikodem Popławski is, at the time of recording, a physicist in his 50s, working at the University of New Haven, originally trained in Poland and then at Indiana University. He has, for about 15 years, been working on a single idea. The idea is small, technical, and, if it is correct, completely changes what we thought we knew about the beginning of the universe. The idea begins with a piece of physics that, in standard general relativity, is set to zero. Standard general relativity, as Einstein formulated it in 1915, and as it has been taught in graduate physics classes ever since, describes space-time as a smooth, curved manifold whose geometry is determined by the mass and energy distributed across it. The geometry has curvature. The curvature responds to the matter. The matter moves along the geodesics of the curvature. This is the standard picture. There is, however, an extension of general relativity, developed by Ailey Cartan in 1922 and refined by Tom Kibble and Dennis Sciama in the 1960s, that adds a second geometric property, torsion. In standard general relativity, torsion is zero. In Einstein-Cartan-Kibble-Sciama theory, torsion can be non-zero if matter carries intrinsic spin-angular momentum. Fermions, the particles that make up ordinary matter, carry intrinsic spin. At ordinary densities, the spin of fermions is randomly oriented and the macroscopic effect on spacetime is negligible. At extreme densities, however, the spins are forced into alignment by the Pauli exclusion principle. At sufficiently high density, Popławski's calculations put this at approximately 10 to the 54th kilograms per cubic meter. The alignment becomes so strong that the torsion contribution to the spacetime geometry stops being negligible. What does the torsion do when it stops being negligible? In Popławski's analysis, the torsion produces a repulsive contribution to the gravitational field, not a positive curvature term that adds to attraction, a negative curvature term that subtracts from attraction. The repulsion grows non-linearly with density. At ordinary densities, the repulsion is irrelevant. At nuclear densities, the repulsion is still negligible. At black hole interior densities, the repulsion becomes comparable to the gravitational attraction. At a critical density, that 10 to the 54th figure, the repulsion equals the attraction. Above that density, the repulsion exceeds the attraction. The collapse stops. The matter rebounds. This is the bounce. In standard general relativity, the interior of a black hole is mathematically a singularity. The collapse of matter inside the event horizon proceeds without limit. The density goes to infinity. The curvature goes to infinity. The equations themselves break down. The standard interpretation has been that this is a sign that quantum gravitational effects, which we do not yet have a complete theory for, take over at the highest densities and prevent the actual formation of an infinite density singularity. The Einstein-Cartan picture proposes that the torsion is, in fact, that quantum effect. The spin-angular momentum of fermions treated classically provides exactly the repulsive force at exactly the density scale where standard general relativity predicts a singularity. The collapse, in Popławski's picture, does not become a singularity. It becomes a bounce. And what happens after the bounce? Here is where the picture acquires its most striking implication. The matter that has rebounded from the bounce continues to expand. The expansion is, mathematically, governed by the Einstein-Cartan field equations with a repulsive torsion term at high density and a normal gravitational term at lower density. As the matter expands and the density drops, the torsion contribution diminishes and the gravitational contribution takes over. The expansion slows. The matter, after the bounce, undergoes a phase of rapid expansion that, in Popławski's analysis, is mathematically indistinguishable from inflation. The bounce produces inflation, naturally, without fine-tuning, without a separate scalar field whose potential has to be carefully arranged, without all the parameter freedom that has, in the standard inflationary picture, made inflation a somewhat awkward fit to the data. After inflation, the expansion proceeds at a rate determined by the matter content. The hot, dense plasma cools. The universe transitions through the standard sequence: quark-gluon plasma, nucleosynthesis, recombination, the cosmic microwave background, the formation of stars and galaxies, the universe we observe today. In Popławski's picture, this entire sequence happens inside the parent universe black hole. The Big Bang is not the beginning of space-time. The Big Bang is the rebound point of matter that had previously collapsed in a parent universe. Our universe is the interior of that black hole. The parent universe still exists in principle, on the other side of the event horizon we cannot see past. We're inside something. The something is a black hole. The black hole sits in a parent universe whose physics we cannot observe. Now I want to slow this down, because I want you to be inside the bounce, not as a metaphor, not as a thought experiment from a textbook, as yourself. Imagine that you are part of the matter that became our universe. You're not yet anyone in particular. You're a distribution of fermions, electrons and quarks in the late stages of a parent universe's history. The parent universe is in many ways like ours. It has galaxies, it has stars, it has black holes. One of those black holes is the one your matter is falling into. You begin the fall slowly. The event horizon is in front of you, but you do not see it the way you see a cliff. You do not feel anything special when you cross it. The geometry inside the event horizon is similar enough to the geometry outside that, locally, you would not notice the transition. What you would notice is that the directions through space have changed. The radial direction toward the center of the black hole is now a temporal direction. You're no longer falling spatially toward the center, you're falling temporally. The future, for you, is the center of the black hole. The past, for you, is the event horizon you have already crossed. You fall. The geometry deepens. The density rises. The temperature rises. You are compressed. The fermions around you are forced into closer and closer alignment by the exclusion principle. The torsion contribution to the space-time geometry, which has been negligible your entire history, starts to become noticeable. At 10 to the 54th kilograms per cubic meter, the torsion repulsion equals the gravitational attraction. Above that, the repulsion exceeds the attraction. The fall, for you, stops. The fall reverses. You are now expanding outward. The expansion is rapid. The expansion is, mathematically, what the standard cosmology calls inflation. You are, for the first time in your existence, travelling outward rather than inward. The geometry that you're inside is changing. The interior of the parent universe black hole is opening into a new universe, your universe, with its own space-time, its own laws, and its own arrow of time. The arrow of time points outward, away from the bounce. Forward, for you, is no longer the centre. Forward, for you, is the direction of expansion. The expansion continues. The density drops. The torsion contribution becomes negligible again. The standard gravitational and quantum field theoretic processes take over. The hot plasma of fermions and bosons goes through the standard sequence. The quark-gluon plasma freezes out. Nuclei form. Atoms form. Stars form. Galaxies form. Slowly, on cosmic timescales, the universe you're now part of becomes the universe you remember from your life. The night sky you see when you walk outside, the Milky Way, Andromeda, the galaxies of the local group, the thousands of other galaxies in the local supercluster, the hundreds of thousands of structures of a large-scale structure beyond. All of it is inside the parent universe black hole. All of it. The 13.8 billion years of expansion since the bounce. The 14 billion light-years of horizon distance. The trillions of galaxies. The hundreds of billions of stars in each. The planets. You. The Big Bang. You've been hearing about your whole life was not a beginning. It was a turnaround. The singularity at the center of the parent universe black hole, which standard general relativity predicts, did not occur. The torsion repulsion replaced it. The collapse became a rebound. The rebound became expansion. The The expansion became inflation. Inflation became the universe. You are inside it. You have always been inside it. The matter you're made of has, in this picture, a continuous history that crosses the bounce. It was matter before the bounce in the parent universe. It compressed. It rebounded. It became matter after the bounce in our universe. The matter is the same. The geometry has changed. Hold this picture for a moment. The pace of the section is meant to be slow. I want you to feel the bounce, not as a violent event, but as a turning. The collapse that did not become destruction. The compression that became expansion. The end that became a beginning, without ever actually being an end. This is the Popławski picture. It is one specific candidate mechanism for how our universe could be inside a black hole. It is not the only one. The Afshoriman-Pourhassan picture, which we will come to in the next part, is different. There are other variants. But Popławski's picture has the virtue of being concrete. It identifies a specific mechanism, the spin-angular momentum of fermions, treated in the Einstein-Cartan extension of general relativity, and a specific density at which the mechanism activates. It predicts a specific behaviour, the bounce, and predicts that the resulting universe inherits the angular momentum of the parent black hole, which would show up at large scales as a preferred axis of rotation. The Shamir result in this picture is the predicted axis. It is not an anomaly. It is a signature. And here is the thing about signatures. They accumulate. We have just seen one, the Shamir rotation asymmetry. There are others, the Schwarzschild coincidence we already covered, the CMB axis of evil we will cover, the Planck low multipole power deficit we will cover. They all bend the same way. They all point at the same kind of geometry. We are inside something. The something has a shape. The shape leaves fingerprints. The fingerprints are starting to show up across multiple independent measurements. The picture is, if you're willing to follow the mathematics, starting to make sense. We're about to step into a parallel branch of the picture, the Afshoriman-Pourhassan picture, which says something even stranger than what we have just walked through. It says we are not in the interior of a black hole. It says we are on the surface of one, a four-dimensional surface of a five-dimensional star. It is a more demanding picture mathematically. It is also, in some ways, an even cleaner fit to the data. Let us walk into that next. Part 7. The Universe as a Surface. In 2013 and 2014, 3 physicists at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, published a sequence of papers that took the universe as black hole picture and pushed it one direction further. Their names are Nyayesh Afshordi, Robert Mann, and Razia Pourhassan. Afshordi is a cosmologist of Iranian-Canadian background, known for his work on dark energy and modified gravity. Mann is a senior theoretical physicist with a long career in black hole physics and quantum gravity. Pourhassan was, at the time, a postdoctoral researcher working with Afshordi. Their proposal, published first in the Journal of Cosmology and Astroparticle Physics, and then summarized in a cover article in Scientific American in September 2014, was deceptively simple. They asked, what if our universe is not inside a four-dimensional black hole in a five-dimensional space, but rather is the four-dimensional event horizon of a five-dimensional black hole? I need to slow down on what that means, because the geometric setup is unfamiliar. Imagine, in the standard picture, a three-dimensional space, the space around you, the room you are in. Now imagine a black hole in that three-dimensional space. The black hole has a spherical event horizon. The event horizon is a two-dimensional surface. Standing outside the black hole looking at it, you see a two-dimensional sphere. The interior of the black hole is a three-dimensional region. The horizon is a two-dimensional boundary. Now imagine going up one dimension. Take a four-dimensional space. 3 dimensions of space plus 1 of time, like the space-time we live in. Imagine a black hole in that 4-dimensional space-time. The event horizon is a 3-dimensional surface, a hypersphere. The interior of the black hole is a 4-dimensional region. The horizon is a 3-dimensional boundary. Now go up one more dimension. Take a 5-dimensional space. 4 of space plus 1 of time. Imagine a black hole in that 5-dimensional space-time. The event horizon is a 4-dimensional surface. The interior of the black hole is a 5-dimensional region. The horizon is a 4-dimensional boundary. The Afshordi-Manpur-Hassan proposal is that our entire 4-dimensional space-time, 3 dimensions of space plus 1 of time, the space-time we live in and measure and do physics in, is the 4-dimensional event horizon of a 5-dimensional black hole. We are not inside it, we are on it. This is a substantially different picture from the Popławski bounce. In the bounce picture, our 4-dimensional universe is the interior of a 4-dimensional black hole. We are deep inside in the temporal direction defined by the geometry. In the Afshordi-Manpur-Hassan picture, our 4-dimensional universe is the surface of a 5-dimensional black hole. We're not deep inside anything. We're spread thin over a higher dimensional structure. The picture is harder to visualize, but it has several attractive features. First, it explains the smoothness of the cosmic microwave background without needing inflation. Inflation, in the standard picture, is invoked to explain how regions of the CMB that should have been causally disconnected can have the same temperature to 1 part in 100,000. The Afshordi-Manpur-Hassan picture explains the smoothness differently. The event horizon of a black hole is, by the geometric definition of an event horizon, a surface that has been in causal contact with itself for the entire history of the parent 5-dimensional star's collapse. The smoothness is not a consequence of inflation. The smoothness is a consequence of the horizon being a horizon. This is, in physics terms, a significant claim. Inflation has been the standard explanation for CMB smoothness for 40-plus years. The Afshordi-Manpur-Hassan picture proposes a different mechanism that produces the same result. If their picture is correct, inflation is not necessary for cosmology. The horizon does the work. Second, the picture predicts small departures from perfect smoothness. The 5-dimensional star whose collapse produces our event horizon would not be perfectly homogeneous. It would have small variations in its density, the way an actual star has small variations in its interior. Those variations would imprint on the event horizon as small variations in the 4-dimensional space-time that we live in. They would show up as the CMB anisotropies we measure, the cold spots, the warm spots, the slight asymmetries. The Afshordi-Manpur-Hassan picture predicts that the magnitude of the departures from smoothness should be at the few percent level. This is roughly the level at which several CMB anomalies, the cold spot, the axis of evil, the low multipole power deficit, have been measured. The match is suggestive. It does not prove the picture. It does not even, by itself, distinguish their picture from other candidates. But the predicted magnitude is in the right ballpark. Third, the picture predicts that the universe should have a preferred direction. The 5-dimensional star whose collapse generates our 4-dimensional horizon would, in general, have a rotational axis. The rotation of the parent star induces a rotation in the horizon geometry. Galaxies forming on the horizon would inherit rotation directions correlated with the parent rotation axis. The Shamir result, in the Afshordi-Manpur-Hassan picture, is also the predicted axis. It is the same prediction as the Popławski bounce picture, arrived at through different geometry. Both pictures predict a preferred axis. Both predict the rotation asymmetry. Both predict roughly the magnitude that Shamir has measured. This is the convergence that makes the rotation result feel weighty. It is not just one theoretical framework that predicts it. It is 2 independent frameworks, developed by different physicists working from different starting points, both predicting the same observational signature. The cosmology community in 2025 is, slowly, beginning to recognize this convergence. Active research programs are studying both the Popławski bounce and the Afshordi-Manpur-Hassan horizon. Calculations are being done to distinguish them. Other calculations are being done to test alternative explanations, primordial vorticity, modified inflation, anisotropic initial conditions. that might explain the rotation result without requiring the universe to be inside or on a black hole. The universe inside or on a black hole pictures are no longer fringe ideas. They are mainstream candidates. The Afshordi-Manpour Hassan paper, when it first appeared, received considerably more attention than Popławski's papers had. The Scientific American cover in September 2014 was titled, "Did a Hyper-Black Hole Spawn the Universe?" The picture entered briefly the public conversation. It then faded back into specialist literature, where it has been quietly developed for the last decade. What is striking is that, in the years since, the observational situation has shifted in their favour. The Planck low multipole power deficit is more securely established. The CMB axis of evil has not gone away. The Shamir rotation result has been added to the inventory. The Afshordi-Manpour Hassan picture in 2014 was supported by approximately 2 anomalies and the Schwarzschild coincidence. The same picture in 2025 is supported by approximately 4 anomalies and the Schwarzschild coincidence. The trend is in their direction. I want to be careful here. The trend is not in itself proof. Cosmology has seen many trends that did not turn out to mean what they initially seemed to mean. Many initially exciting cosmological anomalies have, in the long run, dissolved. But the universe's black hole picture has, in 2025, more observational support than it has ever had. It has the Schwarzschild coincidence, which has been stable for 50 years. It has the CMB axis of evil, which has been stable for nearly 20 years. It has the Planck low multipole power deficit, which has been stable for over a decade. It has the Shamir rotation result, which is the new addition. 4 independent anomalies pointing the same direction. 2 well-developed theoretical frameworks, the Popławski bounce and the Afshordi-Manpour Hassan horizon, that predict exactly this set of signatures. The picture is, by historical standards, on the verge of moving from speculation to candidate explanation. Not from candidate to confirmed, but from speculation to candidate. That is a step. A step is a real change in the standing of an idea. And the step has happened, quietly, in 2025. We're now going to pull back and look at the 4 anomalies together, because the strength of the case is not in any one of them. The strength is in the convergence. 4 small earthquakes do not make a single large one, but 4 small earthquakes, all along the same fault line, all displacing in the same direction, suggest that the fault line is real and that something is moving along it. That is the situation we are in cosmology, in 2025. Let us look at the 4 together. The rotation asymmetry, the Schwarzschild coincidence, the axis of evil, the low multipole deficit, each one a small puzzle, together a shape. The shape is what we're going to look at next. Part 8. The 4 anomalies that bend. The same way. When physicists talk about anomalies, they usually mean small, specific, well-documented departures from what a theory predicts. Anomalies are not, in themselves, refutations. A single anomaly, at the 2 or 3 sigma level, is usually noted, investigated, and either explained or quietly forgotten over the course of a few years. The history of physics is full of small anomalies that turned out to be real artifacts of measurement, or systematic effects that had been overlooked, or genuine statistical flukes that did not survive larger samples. Most anomalies are not, in the end, signs of new physics, but occasionally a set of anomalies appears that does not behave like a normal collection of small puzzles. The set has internal coherence. The anomalies bend in the same direction. They support each other. They predict each other. They are, in the language physicists sometimes use, conspiratorial. They behave as if they have a common cause, even before that cause has been identified. The 4 anomalies we are about to walk through are conspiratorial. They have, in 2025, accumulated enough collective weight that they have begun to define a research program. The research program is to figure out whether they are, in fact, separate accidents that happen to bend the same way by chance, or whether they share a common cause. The universe inside or on a black hole picture proposes that the common cause is real and is the inheritance of geometry from a parent black hole. The standard inflationary picture proposes that the common cause does not exist, and that the four anomalies are independent statistical artifacts. Let me walk you through each one, then we will look at what the combination implies. Anomaly 1, the Shamir rotation asymmetry. We have already covered this in detail. 263 spiral galaxies in the JWST JD's deep field, classified for rotation direction. 158 rotate one way, 105 rotate the other way. The split, 60% versus 40%, is well outside what an isotropic universe should produce in a sample of this size. The asymmetry has been reproduced at lower redshift in Sloan and Pan stars. The classification algorithm has been tested against blinded human observers and against randomly mirrored images. The asymmetry survives every cross-check. Statistical significance well above 3 sigma, published in monthly notices of the Royal Astronomical Society in March 2025. Anomaly 2, the Schwarzschild coincidence. The mass of the observable universe, somewhere around 10 to the 54th kilograms, when plugged into the Schwarzschild formula R equals 2gm over c squared, gives a radius approximately equal to the radius of our cosmic horizon, approximately 14 billion light-years. The match is to within order unity, which in physics is the threshold below which numerical agreements are considered potentially meaningful rather than purely coincidental. The match has survived every revision of cosmological parameters since 1972. Dark matter was added. The match held. Dark energy was added. The match held. The Hubble constant has been revised several times. The match held. 50 years of measurement, 50 years of recalibration, and the same numerical agreement continues to apply. Anomaly 3. The cosmic microwave background axis of evil. This is a more technical anomaly, and it deserves a moment of explanation. When you map the temperature of the cosmic microwave background across the entire sky, you can decompose the map into spherical harmonic modes, which are roughly the spherical analogue of Fourier modes for ordinary functions. The lowest modes, the quadrupole, the octupole, describe the larger scale features of the map. In an isotropic universe, the directions of the principal axes of these modes should be statistically random. They should not align with each other. They certainly should not align with anything in particular in the local universe. When Planck mapped the CMB in 2013 and 2018, the quadrupole and octupole modes were found to be aligned with each other, to a precision that should occur by chance only a few % of the time. They were also aligned with a similar precision, roughly with the ecliptic plane of our solar system, which is, on the scale of the universe, an absurd alignment to find. The CMB does not, in any plausible mechanism we have proposed, know about the ecliptic plane of our solar system. The ecliptic plane is a local feature set by the formation of our planetary system 4.6 billion years ago. The CMB was emitted 380,000 years after the Big Bang 13.8 billion years ago. There is no causal connection. The axis of evil, which is the somewhat dramatic name given to this alignment, has been investigated extensively. Some authors have argued that it is an artifact of the foreground subtraction used to clean the CMB maps. Galactic dust, galactic synchrotron emission, and other foreground sources are subtracted from the raw measurements to produce the CMB map. If the subtraction is imperfect, it could imprint residual structure on the cleaned map that correlates with the ecliptic plane. This is a respectable objection. It has not, however, fully resolved the anomaly. Detailed studies have found that, even after multiple independent foreground subtraction methods, the alignment persists at a statistically significant level. The axis of evil is, in the universe's black hole picture, a natural prediction. A rotating parent black hole would induce a preferred axis in the interior geometry, and that axis would show up in the CMB as well as in galaxy rotation. The CMB axis and the galaxy rotation axis do not, as of 2025, point in exactly the same direction, but they are in the same hemisphere, which is more than chance would predict, and the precise alignment depends on calculations that are still being refined. Anomaly 4. The Planck Low Multipole Power Deficit. This is the most technical of the four, and the one that, ironically, has the cleanest statistical significance. When you plot the power spectrum of the CMB, the strength of the temperature fluctuations as a function of angular scale, the standard inflationary model predicts a specific shape. The shape rises from low angular scales to a peak at around 1 degree, then falls off at smaller scales. The general shape has been confirmed by every CMB experiment, from Kobe in the 1990s to Planck in the 2010s. But the very lowest multipoles, the quadrupole, the octupole, and a few others, have less power than the standard model predicts. The deficit is small. It is at the 2 to 3 sigma level, depending on which modes are considered and how the statistical analysis is done. The low multipole deficit by itself is not a discovery. It is the kind of mild tension that often disappears on closer examination. WMAP saw it. Planck confirmed it. The next generation of CMB experiments, CMBS-4, Simon's Observatory, Light Bird, will measure it with greater precision. By the early 2030s, we will know whether the deficit is real or whether it was a fluctuation that has gone away in higher quality data. But the deficit, while small, is exactly what the universe's black hole picture predicts. A closed, finite universe, which is what you get if you're inside a black hole, has a maximum spatial scale. Modes whose wavelengths exceed that maximum scale do not fit inside the universe and are absent from the observed power spectrum. The deficit is the expected signature of a finite closed cosmology. In the standard infinite inflationary cosmology, the deficit is an unexplained anomaly. In the black hole interior picture, the deficit is a prediction. So now we have all four anomalies on the table. Let us put them side by side. Anomaly 1, rotation asymmetry, predicted by both the Popławski bounce and the Afshordi-Mann-Pourhassan horizon. Not predicted by the standard inflationary model. Anomaly 2, Schwarzschild coincidence, predicted by both the Popławski bounce and the Afshordi-Mann-Pourhassan horizon. Not predicted by the standard inflationary model. Anomaly 3, CMB axis of evil, same. Anomaly 4, low multipole power deficit, same. All four, same direction, same prediction, same explanation. This is, in physics, what a conspiracy looks like, not in the popular sense, in the technical sense, a set of independent anomalies, in independent observations, in independent measurement contexts, all of which point at the same underlying picture, all of which are predicted by the same theoretical framework, and none of which is predicted by the standard model. The conservative response to a conspiracy is to assume it is coincidental. Four independent anomalies, each individually weak, can by chance bend the same way. The probability is not zero, it is small. How small depends on how you define the search space and what you count as an anomaly, but rough estimates put it somewhere in the range of 1 in 100 to 1 in 1,000. Not impossibly small, but also not the kind of probability that, when faced with it, you can comfortably set aside without a counter-explanation. The alternative response is to take the convergence seriously, to say, four anomalies all bending the same way, all predicted by the same picture, all explained by the same mechanism, are not four anomalies. They are one signature, expressing itself through four different channels. The signature is the geometry of the parent black hole. The channels are the rotation of galaxies, the size of the universe, the alignment of CMB modes, and the power deficit at the lower scales. They are not four problems. They are one solution showing through in four places. Which response is correct depends, in the end, on the data. More data, larger samples, higher precision measurements. The next decade will produce all three. The Vera Rubin Observatory's LSST will catalogue billions of galaxies, providing a sample size for rotation classification thousands of times larger than the JADE sample. The Euclid mission, whose first data release was in 2024, will map the large-scale structure of the universe with unprecedented precision. The Roman Space Telescope, launching in 2027, will measure weak gravitational lensing across vast areas of sky. CMB-S4 will measure the polarization of the cosmic microwave background with sufficient precision to distinguish inflationary from non-inflationary signatures. By the early 2030s, the picture will be clearer. Either the four anomalies will sharpen into a coherent signal that demands the black hole interior interpretation, or they will dissolve back into the noise of normal statistical fluctuation. The question, for the first time in 50 years, has a timeline. The waiting will end. The data is coming. But here, in 2026, on the night you're listening to this, the situation is what it is. Four anomalies, same direction. Two theoretical frameworks predicting them. One standard model that does not. The picture is no longer fringe. The picture is, with some humility about its remaining uncertainties, a candidate explanation for what cosmology actually sees when it looks at the universe at the larger scales. We're inside something. The something has fingerprints. The fingerprints are starting to appear. 4 of them so far on 4 different surfaces. More will come, or fewer. The next decade will say, we are now going to leave the data behind for a while. We have looked at what the observations show. We have looked at what the theories predict. We have looked at the convergence and what it implies. Now we are going to step into the picture itself. We are going to stand at the horizon. We are going to look at what it means, if all of this is right, to live inside an event horizon. Because the horizon is the strange part. The horizon is the part that, when you sit with it, changes how the universe feels. Not in some abstract way, in a very direct, very immediate, very personal way. The universe you have been looking at your whole life, the night sky, the stars, the planets, the galaxies you cannot see but know are there, is, in this picture, the inside of a one-way membrane. There is an outside. You cannot see it. You will never see it. From where you stand, the outside does not exist. It is not dark. It is not blank. It is not anything from your vantage. It is the part of the universe that for you is not. That is the next thing we have to look at. Let us walk to the horizon. Part 9. At the horizon. Imagine you're standing at the cosmic horizon, the boundary at the edge of what you can see, 14 billion light years from where you started, give or take a few. There is no actual standing involved, because you cannot reach the horizon, but the geometry permits the thought experiment. So go there. Stand there. Look outward. There is nothing. I do not mean blackness. Blackness implies an absence of light against a presence of something. I do not mean emptiness, because emptiness implies a space inside which things could be, but are not. I mean nothing. From your position at the horizon, the outward direction does not contain anything that can affect you. Light cannot reach you from out there. Matter cannot reach you from out there. Information of any kind cannot reach you from out there. The outward direction is, for you, a direction that does not exist. This is true in standard inflationary cosmology too. The cosmic horizon marks the boundary beyond which the universe is expanding faster than light can cross the expansion. But in the standard cosmology, the universe is presumed to continue past the horizon. There is more out there. Other observers at different locations see different portions of the same larger structure. The horizon is observer-dependent. The universe as a whole is larger than what any single observer can see. In the universe's black hole picture, this changes. In the Popławski bounce picture, our cosmic horizon is also an event horizon. The same surface that limits what we can see is the surface that defines the boundary of the black hole interior we are inside. Past that surface, in the temporal direction, is the parent universe. Past that surface, in the spatial direction, there is no past that surface in the spatial direction. The geometry closes on itself. In the Afshordi Manpur Hassan horizon picture, our 4-dimensional space-time is itself the surface. There is no past it in any direction we could possibly travel in. The 5th dimension exists, but we cannot move into it. The interior of the 5-dimensional black hole exists, but we are not in it. We are the horizon. Either way, the conclusion is the same. We are inside something. The thing has a boundary. The boundary is one way. We cannot, even in principle, send information through it. Sit with this for a moment. The universe you have lived in for your entire life has, on the geometric picture we're considering, a hard outer edge. Not a soft edge that future telescopes will resolve. A hard edge that the geometry itself forbids you from crossing. The edge is shaped like a sphere centered on you. The sphere is also centered on every other observer in the universe. Every observer has their own horizon, all of which are geometrically equivalent, but from your vantage, the sphere is centered on you. The sphere has a radius of approximately 14 billion light-years. The sphere is the boundary. Outside the sphere, in the language of the standard cosmology, there is more universe. In the language of the black hole interior cosmology, there is a parent universe whose physics is, in principle, completely inaccessible. In either case, you cannot reach it. You cannot send a signal to it. You cannot receive a signal from it. From your position inside the sphere, the outside might as well not exist. Now ask yourself, would this feel different than what it feels like to be inside an ordinary universe? The answer is no. You would not feel anything special. The universe inside the horizon is, from your vantage, exactly what an ordinary universe would be. Stars, galaxies, days, lives, people, everything. The boundary is invisible, because the boundary is exactly where the visibility ends. You cannot see the boundary because anything close enough to the boundary to be seen has its light redshifted to wavelengths your eye cannot detect, and anything past the boundary you cannot see at all. This is the deep strangeness of being inside an event horizon. It does not feel like anything. The geometry that surrounds you does not announce itself. The constraint that you can never reach the outside does not, in your daily experience, manifest as anything you can notice. The universe simply is what it is, from your perspective. Galaxies rotate, stars are born and die. The night sky changes slowly. You go on with your life. Hold this realization for a long moment, because it is, I think, the first emotional weight of the whole video. If we have been inside a black hole this entire time, then nothing about our experience would have told us. The universe does not feel like it is inside something. The galaxies do not feel like they are nested. The expansion does not feel like it is constrained. Everything feels like ordinary cosmology, because ordinary cosmology is what being inside the event horizon of a black hole, from inside the event horizon, looks like. You have not lost anything. You have not been deceived. The universe is exactly what you thought it was. The stars are still bright. The galaxies still spin. The planets still orbit. The flowers still grow. The seasons still turn. You're still yourself. The only thing that has changed is the frame around it. Before tonight, perhaps you thought of the universe as an infinite expanse, with our observable patch being only the small fraction we can see. After tonight, you might consider the possibility that the universe is instead a finite volume bounded by a one-way surface. Same stars, same galaxies, same flowers, different frame. The frame does not change anything about your experience, but it does change something about how the experience sits in your mind. The expansion you have always known to be accelerating becomes, in the new frame, the slow growth of a sealed interior. There is no escape. There never was. There never will be. The boundary has always been there, and it has always been one way, and you have always been inside it. You did not know. You could not know. From inside, the inside is everything. I want to sit with this for a long moment, because the realization is, in some way, the central emotional content of the entire universe's black hole picture. It does not change anything visible. It changes everything about the position the visible takes inside the invisible. We are inside something. I planted that phrase at the start of the video. I want to bring it back here now, in the context of the horizon. The phrase, then, was an opening statement. It was a hypothesis. We are inside something. Maybe. The phrase now is something different. The phrase now is a description of where we are standing. We are inside something. The something has a one-way boundary. The boundary is approximately 14 billion light-years from any observer in any direction. Inside the boundary is everything we have ever known. Outside the boundary is everything that, from our position, does not exist. The picture is, in this way, both unsettling and oddly calming. Unsettling because the universe is smaller than we thought. Calming because the smaller universe is, on its own terms, complete. The inside has been our entire experience. The inside has been enough. The inside contains stars, galaxies, planets, life, you, me, this evening, this question. The inside is not lacking anything you have ever needed, and here is perhaps the gentlest implication. If we have always been inside something, and we did not know it, and it did not affect us, and it never will affect us, then knowing it now does not have to change anything. The universe is what it is. The picture is the picture. The boundary is the boundary. We live our lives. We go to sleep at night. We wake up in the morning. We do what we have always done. The frame, once you have considered it, can go back into the background of your mind. The frame is just a frame. The contents are the contents. The contents have not changed, but the contents include a quiet new fact now. The contents include the fact that you, the listener, exist inside an enclosed cosmic structure whose geometry you have just walked through. The contents include the fact that the universe satisfies an equation that defines a black hole. The contents include the fact that your matter, the carbon and oxygen and hydrogen in your body, is part of the mass that satisfies the equation. You have been counted. That is, in a way, what tonight is about. Not whether we are inside a black hole. The math says increasingly that we might be. Not what to do with the information. The information does not require us to do anything. But the fact of having considered the question. The fact of having sat with the geometry. The fact of having stood, even in imagination, at the horizon, and looked outward, and noticed that the outward direction is, from your position, a direction that does not contain anything. That is the quiet weight. That is what we carry with us when we leave this section. We have one more long stretch in front of us. We are going to ask, in the next part, what it would mean for every black hole in our universe to be the entrance to another universe just like ours. The recursion, the Sagittarius A implication, the cosmic nesting. We are going to walk into that. It is, in many ways, the strangest section of the night. But for now, we have stood at the horizon. We have seen that the boundary is invisible because it is the boundary of visibility. We have considered that the universe inside the boundary is exactly what we have always known, and we have, perhaps, accepted that being inside something, in this case, is the same thing as being. The inside is all there is, for us. The inside is enough. We are inside something. The phrase, by the end of this section, has acquired its second meaning, not as a hypothesis, as a quiet recognition that we have, this whole time, been inside, and the inside has been our home. Let us walk now to the recursion. Let us walk to the doorway in our own galaxy. Let us walk to Sagittarius A. Part 10. Every black hole, a doorway. I want to start this section gently, because the implication we are about to walk through is, in a certain way, the strangest thing the universe's black hole picture says. The implication is not strictly required by the mathematics. The mathematics permits it, does not force it, and does not forbid it. But once you have accepted the premise that our universe is the interior of a black hole, the implication arrives almost automatically, and once it arrives, it is difficult to set aside. The implication is this: if our universe is inside a black hole, then every black hole in our universe is plausibly the inside of another universe. The mass of the universe satisfies the equation that defines an event horizon. We covered that. The equation is the Schwarzschild equation. The equation applies, in standard general relativity, to all black holes, not just to the universe's black hole geometry. To every black hole, every black hole satisfies R equals 2gm over c squared, the relationship is universal. So when we look at, for example, the black hole at the centre of the Milky Way, Sagittarius A, a 4 million solar mass black hole sitting 26,000 light-years from Earth at the dynamical centre of our galaxy, we are looking at an object that satisfies the same equation as our cosmic horizon. The Schwarzschild radius of Sagittarius A, given its mass, is approximately 12 million kilometres. That is the size of its event horizon. Anything inside that radius cannot by the geometry escape outward. In the standard picture, the interior of Sagittarius A is a region of progressively higher curvature culminating in a singularity at the centre. The interior is, mathematically, a singularity hidden behind an event horizon. Whatever falls in is, by standard general relativity, compressed without limit toward the central point. Nothing comes back out. In the Poplawski picture, the interior is not a singularity. The interior is, at sufficiently high density, the site of a torsion-driven bounce. The bounce produces a rebound, which inflates outward into a new space-time. The new space-time is a new universe. The new universe is geometrically sitting inside Sagittarius A. From our vantage outside Sagittarius A, we cannot see this new universe. The event horizon blocks our view. But the new universe is, in this picture, there. It has its own age, its own contents, its own observers, its own physicists arguing about whether they are inside a black hole. Sagittarius A has been there, in our sky, for as long as anyone has looked at the sky. It is older than humanity. It has accreted matter from the galactic centre for billions of years. In the standard picture, the matter that has fallen into Sagittarius A has been destroyed at the singularity. In the Poplawski picture, that matter has, at high density, bounced and become the matter content of a new universe sitting inside the event horizon. There is a cosmos inside Sagittarius A. From our vantage, the cosmos is invisible. From inside the cosmos is everything. I want to slow down on this, because the implication is genuinely strange and deserves to be taken seriously rather than rushed past. The Milky Way has, by current best estimates, somewhere around 40 to 100 million stellar mass black holes scattered through its disk and halo. These are the remnants of massive stars that ended their lives in supernova explosions and collapsed their cores into black holes. Each one has a mass of roughly 5 to 50 solar masses. Each one, in the Poplawski picture, is a candidate seed for another universe. The interior of each one would, given the right density conditions at the bounce, have inflated into a new space-time with its own physical laws, its own contents, its own observers. Other galaxies have much more massive central black holes. M87's central black hole, the first imaged directly by the Event Horizon Telescope in 2019, is 6.5 billion solar masses. The most extreme candidates, TON 618 and Phoenix A, approach 100 billion solar masses. In the Poplawski picture, each one is, plausibly, a doorway into a separate cosmos. Once you start the recursion, there is no obvious place to stop. If we are inside a parent universe's black hole, that parent is plausibly inside a grandparent's. The series goes on. It is not strictly required by the theory. The theory permits a universe to be inside a black hole without requiring the parent to be inside one. But the theory does not provide a natural stopping point. The simplest version of the picture is one in which the recursion does not terminate. This is, in 2025, an active area of speculation. Some physicists take it seriously, others think it is too speculative. The recursion is, like much of the broader picture, a consequence of the underlying premise rather than a strongly supported claim. But it is worth considering because it changes how black holes feel. Black holes, in our standard understanding, are the most extreme objects in the universe. They are objects of pure gravity, around which matter is destroyed and from which nothing escapes. They are the endpoints of stellar evolution for the most massive stars. They are the seeds at the centres of galaxies. They are, in a sense, the most thoroughly inhuman objects in the cosmos. They are not places, they are conditions. In the universe as black hole picture, black holes acquire a different role. They are not endpoints, they are continuations. The matter that falls into a black hole does not, in this picture, vanish. It becomes the matter of a new universe. The new universe has its own history, its own evolution, its own galaxies, its own stars, possibly its own observers. The black hole is not the death of the matter that falls into it. The black hole is a doorway. The doorway leads into a new cosmos. This is, in a certain way, the most affirmative implication of the entire picture. The standard picture of black holes is one of cosmic annihilation. Matter falls in, matter is destroyed, information is lost, or, in modern unitary treatments, somehow preserved in scrambled form on the horizon but irretrievable in any practical sense. The picture is one of finality. Black holes are where things end. The Popławski picture replaces the finality with continuity. The matter that falls into a black hole does not end. It becomes the seed of a new universe. The new universe is not, from our vantage, accessible. The event horizon blocks our view. But it is, from its own vantage, an entire cosmos. New stars form, new galaxies form, new planets form, possibly eventually new life forms. New observers look up at their night sky and ask the questions we ask. They run their own calculations. They discover their own Schwarzschild coincidences. They argue with each other about whether they are inside a black hole. They are. I want to put you gently into Sagittarius A. Not as a metaphor, not as a thought experiment with a punchline, as yourself, slowly approaching the central black hole of the Milky Way on a trajectory that, in the Popławski picture, leads not to your destruction but to your emergence in a new cosmos. You are, in this thought experiment, on a long inward trajectory. Sagittarius A is 26,000 light-years away from Earth. The trip, even at the speed of light, would take 26,000 years. You're not literally making this trip. The thought experiment makes the trip in an instant. You're now near the event horizon. The black hole is in front of you. It is, from this distance, a featureless dark sphere against the background of the galactic centre, where the dense stellar field has been visibly distorted by the gravitational lensing of the black hole's mass. The sphere is roughly 12 million kilometres across. You're approaching at low speed. The black hole grows in your field of view. You cross the event horizon. Locally, you notice nothing. The geometry is smooth across the horizon. Your instruments do not register a discontinuity. The light from outside the horizon, behind you, is still arriving for now, though its frequency has shifted in ways your detectors register. The light from inside the horizon, ahead of you, looks the way light always looks. You're inside the black hole. You did not notice the crossing. You continue inward. The geometry deepens. The radial direction toward the centre is now, in the local geometry, a temporal direction. You're no longer falling spatially toward the centre. You're falling temporally. The centre of the black hole for you is the future. Your future. There is no other future for you now. You continue. In the standard picture, you would now be heading toward the singularity at the centre, which would crush you at finite proper time into a region of infinite density. In the Popławski picture, you do not reach a singularity. You reach the bounce density, 10 to the 54th kilograms per cubic metre, and the matter around you rebounds. The rebound becomes a new expansion. The new expansion becomes a new cosmos. You are now in a new universe. Behind you, in the temporal direction, is the bounce. In front of you, in the temporal direction, is the future of this new cosmos. The new cosmos has its own arrow of time, its own physical laws, its own contents. The contents include, eventually, stars, galaxies, planets. Possibly, in some corner of this new cosmos, observers like you. You did not pass through any boundary. You did not see anything that looked like a doorway. You simply went deeper into Sagittarius A and emerged on the other side of a bounce in a place that, from inside, looks like a universe. There is, in this picture, no death, only transition. The matter you were made of is now the matter of a new cosmos. The new cosmos goes on. New observers come into being inside it. They look up at their sky. They ask the same questions you asked. I want you to hold Sagittarius A in your mind now, slightly differently than you held it before. Before, it was the supermassive black hole at the centre of our galaxy, an object of pure destruction. Now, perhaps, it is something else, a doorway, the nearest other universe to our own, sitting 26,000 light-years away, holding our galaxy together with its gravity. The thing that keeps us in our galaxy is also, in this picture, the entrance to another cosmos. I have planted a phrase twice already tonight. The mass of the universe satisfies the equation that defines an event horizon. I planted it during the Schwarzschild coincidence calculation. I am bringing it back now in this section because its meaning has shifted. Before, the phrase described a numerical curiosity. Now, the phrase describes a generative process. The mass of the universe satisfies the equation, and the equation applies to every black hole. Therefore, every black hole in our universe contains a universe whose mass also satisfies the equation. Therefore, the equation is not a coincidence. The equation is the mechanism by which universes propagate. If the picture is right, the universe is not unique. The universe is one node in a vast, possibly infinite network of universes connected by black holes. Each black hole in each universe is a doorway. Each doorway leads to a new cosmos. Each new cosmos has its own black holes, each of which is a doorway. The network has no center. The network has no boundary. The network is, in a certain sense, what existence is. We sit, you and I, in one node of this network. The node is our universe. The node has its own black holes. The black holes are doorways into other nodes. Each of those nodes has its own black holes leading to other nodes. The network goes on. The network is, in this picture, what we mean when we say everything. This is, of course, speculation. The Popławski mathematics permits the recursion. The Popławski mathematics does not require it. The Afshordiman Pour Hassan picture supports something similar. There may be other versions. The picture, as of 2025, is not testable in its most ambitious form. The recursion may end at one level. It may end at 5. It may not end at all. We cannot know. But here, sitting in our one universe, on our one planet, on this one evening, the implication is what it is. If we are inside a black hole, then there are universes inside our black holes. The black holes are not where matter ends. The black holes are where matter goes next. The mass of the universe satisfies the equation that defines an event horizon. The equation generates universes. The generation goes on. We're now going to step back. We have considered the 4 anomalies. We have stood at the horizon. We have considered the recursion. We have looked at, in the most ambitious version of the picture, what black hole cosmology says about the broader structure of existence. We have done the hard work of the night. The remaining sections are about what comes next, the next telescopes, the next surveys, the next decade, the window we live in. The question, by 2035 or so, will be answered. The waiting is going to end. The data is coming. But before we get to that, hold the recursion for a quiet moment longer. Black holes are doorways. The matter that falls in becomes something new. The something new is a cosmos. The cosmos contains eventually stars and life and observers. The observers are us, in some other version, or somebody who, like us, asks whether they are inside a black hole. And the answer from inside is, it does not feel like anything in particular. It feels like a universe. It feels like home. Let us walk now to the future, to the telescopes, to the timeline. Part 11. What the next telescope will decide. A question that has been open for 50 years is, by historical standards, an old question. Many old questions in physics have stayed open for much longer. The nature of dark matter has been open since the 1930s. The nature of dark energy has been open since the late 1990s. The complete reconciliation of general relativity with quantum mechanics has been open since the 1960s. The universe's black hole question is, in the company of those, middle-aged but not yet senior. What is unusual about the universe's black hole question in 2025 is that it is, for the first time, on a timeline. The next decade of observational cosmology has been carefully planned, with a sequence of instruments designed to probe exactly the kinds of large-scale features that distinguish the universe's black hole picture from the standard isotropic Big Bang. By the early 2030s, those instruments will have produced datasets that are orders of magnitude larger and orders of magnitude more precise than anything we have now. The question will almost certainly be answered one way or the other. Let me walk you through what is coming. The Euclid mission, launched by the European Space Agency in July 2023, released its first major dataset in 2024. Euclid is a 6-year mission designed to map approximately 1/3 of the entire sky, surveying weak gravitational lensing and large-scale structure with precision that previous wide-area surveys could not approach. By the time Euclid completes its primary mission in 2029, it will have produced a 3-dimensional map of approximately 1.5 billion galaxies, spread across a substantial fraction of the observable universe. The map will allow precision tests of large-scale isotropy. If there is a preferred axis in the universe at large scales, Euclid will see it. If there is no preferred axis, Euclid will rule one out. The Vera Rubin Observatory in Chile began its primary science survey called the Legacy Survey of Space and Time, or LSST, in late 2025. The Rubin survey will observe the southern sky every few nights for 10 years. By the time the survey completes, it will have catalogued approximately 20 billion galaxies, a sample size nearly 15 times larger than Euclid's. The same kinds of large-scale anisotropy tests that Euclid will perform, Rubin will perform on a vastly larger sample. The Shamir rotation asymmetry, if it is real, will be confirmed or refuted by Rubin's complete galaxy catalogue. The 263 galaxies in the JD sample will be matched against, eventually, billions of galaxies in Rubin's. If the asymmetry is genuine, it should appear in the Rubin sample at extremely high statistical significance. If it is not genuine, it will dilute back to 50-50 in the larger sample. The Roman Space Telescope, a NASA mission scheduled for launch in 2027, will perform a high-precision weak lensing survey across a large area of sky. Roman's lensing measurements will be sensitive to any preferred direction in the universe at scales between Euclid's and Rubin's, providing a third independent test of the rotation result and the related anomalies. The CMB-S4 experiment, a ground-based array of telescopes in Chile and Antarctica scheduled to begin operations later this decade, will measure the polarization of the cosmic microwave background with precision sufficient to distinguish inflationary from non-inflationary signatures. The same data set will measure the lowest CMB multipoles with greater precision than Planck. If the low multipole deficit is real, CMB-S4 will confirm it. If it is not, CMB-S4 will dissolve it back into the noise. The axis of evil will similarly either sharpen or disappear. Lightbird, a Japanese-led satellite scheduled for launch in the late 2020s, is specifically designed to detect the polarization signature of primordial gravitational waves generated during inflation. If Lightbird detects this signature, the inflationary picture is strongly supported. If it does not, alternatives to inflation, including the Afshoriman-Purhasan horizon picture, become more attractive. The Simons Observatory will complement CMB-S4 and Lightbird at intermediate angular scales. The Square Kilometre Array, an international radio telescope array under construction in South Africa and Australia, will perform deep surveys of neutral hydrogen across cosmological distances, providing a 3-dimensional map of large-scale structure complementary to Euclid and Rubin. By the early 2030s, all 4 of the anomalies that currently support the universe's black hole picture will have been tested with datasets orders of magnitude larger and more precise than what we have now. The conservative expectation is that some will survive and some will dissolve. The aggressive expectation is that they will all survive. The truly aggressive expectation is that new anomalies, currently below our detection threshold, will emerge, additional fingerprints of the parent geometry, and that those will tip the scales decisively. Whatever the outcome, the question will no longer be open. Either the universe's black hole picture will be supported by an overwhelming amount of converging observational evidence, in which case it will move from candidate to consensus, and the standard inflationary Big Bang model will be modified or replaced, or the anomalies will dissolve, and the universe's black hole picture will be relegated to the historical curiosity status it occupied between 1972 and 2025. This is, in a quiet way, an extraordinary thing to know about a question. Most of the great open questions of cosmology do not have deadlines. The nature of dark matter has been open for nearly a century, and we still do not have a clear deadline for resolving it. The nature of dark energy may be open indefinitely. The reconciliation of general relativity and quantum mechanics may be open for another century or longer. These are questions that the next telescope cannot decide. They require fundamentally new theoretical frameworks, which arrive on their own timeline. The universe's black hole question is different. The picture makes specific predictions. The predictions are testable with instruments that already exist or are under construction. The data will be in within 10 years. The question, in a real sense, is going to be answered in our lifetime. Not answered in the sense that all details will be filled in. Answered in the sense that we will know whether the picture is broadly right, whether the four anomalies are real or not, whether the universe has a preferred axis or does not, whether we are inside something or not. This is a peculiar position for a question to be in. It is the position of a hypothesis that has waited 50 years for the technological infrastructure to test it, and is now seeing the infrastructure come online in real time. The waiting was the hard part. The instruments are funded, the teams are working, the data is going to be in. In 1972, when Patria published his paper, the technological infrastructure to test his hypothesis did not exist. There was no precision CMB experiment. There was no JWST. There were no large galaxy surveys at deep redshifts. The hypothesis was untestable. It was by necessity philosophical. In 2025, the hypothesis acquired its first piece of observational support, the Shamir rotation result. The hypothesis became, for the first time, empirical. It was no longer purely philosophical. It was a hypothesis with a piece of data attached. By 2035, the hypothesis will be testable in a much stronger sense. The aggregate of data from Euclid, Rubin, Roman, CMB S4, Light Bird, Simon's Observatory, SKA, and whatever else comes online in the late 2020s and early 2030s will provide overwhelming statistical power to either support or refute the picture. The hypothesis will move from interesting candidate to either confirmed or rejected. The waiting will be over. We sit, you and I, in the 10-year window between these two states. The question is open. The data is starting to come in. The instruments are being calibrated. The teams are working. By the end of the decade, the answer will be in. I want to call this what it is. It is a privilege. Most questions of fundamental cosmology do not have deadlines, and we are not, as humans, often present for the moment a deep question gets answered. The cosmological constant problem, the dark matter problem, the quantum gravity problem, these may not be answered in our lifetimes. They may take centuries. The universe's black hole question will almost certainly be answered in ours, not in 20 years, in 10. We will, you and I, live to see whether the question turns out to have the answer it currently appears to be leaning toward. This is, I think, the gentlest weight of the whole video. The question is real. The question has a timeline. The answer is on its way. And we, the people listening tonight, get to be alive in the small window between the asking and the answering. We get to hold the question in the open state. We get to sit with the not knowing. We get to wonder. In 20 years, when the answer is in, the wondering will be over. Either the answer will be yes, and children will grow up learning the universe's black hole picture the way you grew up learning the Big Bang. Or the answer will be no, and the picture will be a historical footnote. Either way, the open state of the question, the state we're in tonight, will be over. So we hold it now. We hold it carefully. We listen to the calmness of the question being open, and we know that the calmness will not last forever. The waiting is precious. The not knowing is precious. The question, while it remains open, is a kind of gift. Hold the 4 words once more. We're inside something. By now, perhaps, they feel less like a frightening claim and more like a quiet, settled observation. The inside has been our home. The inside is enough. And we are, for tonight, here. Let us bring it home. Part 12. The window we live in. A few things to gather before the end. The James Webb Space Telescope launched on December 25, 2021. It was supposed to reveal the early universe. It has done that. In the 4 years since launch, it has resolved galaxies at redshifts no previous telescope could reach. It has, in the JWST survey, given us the deepest catalogue of galaxies ever assembled. And in 2025, it gave us 263 spiral galaxies whose rotation directions, when carefully counted, did not balance. This is, in a way, exactly what JWST was designed to do. Not specifically. No one designing Webb in the 1990s was thinking about black hole interior cosmology. But generally, the telescope was designed to look back far enough and clearly enough to find features in the early universe that previous instruments had not been able to see. The job included finding things we did not expect. What we do with what Webb found is up to us. We can dismiss the asymmetry as an artifact. We can fold it into the standard model with modifications to inflation. Or we can take it as the first observational support for 50 years of mathematically respectable speculation about the universe being inside a black hole. The data permits all 3 responses. The data does not by itself force any of them. What I have tried to do tonight is walk you through the case carefully. The Shamir result is a real result in a real journal that has survived real peer review. The interpretations are contested. The black hole interior cosmology is one candidate, with 2 well-developed theoretical frameworks behind it. The standard inflationary model, with modifications, is another. The next decade of telescopes will decide. We're in the small window, the window where the question is open, the window where the answer is being prepared but has not yet arrived. The window where the not knowing is, itself, a precious feature of our position in cosmic history. I want to plant the closing reflection now, because the night is winding down, and I want you to carry it gently with you, whether you fall asleep before the end or stay with me to the last sentence. We're inside something. I said this several times tonight. I want to say it one more time, in its final meaning. In the opening of the video, the phrase was a hypothesis. We might be inside something. The question was rhetorical. We did not know. The picture was speculative. In the middle of the video, after the calculation, the phrase was an observation. We satisfy the equation that defines an event horizon. We probably are inside something. The picture was supported by the math. At the horizon, the phrase became an admission. From inside, the inside is everything. We're inside something, and the something is exactly the universe we have always known. The frame has changed, but the contents have not. The picture became, in a quiet way, a settling. At the recursion, the phrase became generative. We are inside something, and inside the somethings inside us are more somethings. The mass of the universe satisfies the equation, and the equation generates universes, and the universes generate equations, and the equations generate universes. The picture became, in this section, an ongoing process. The universe is one node in a network of universes propagating themselves through black holes. The universe is, in this sense, fertile. It makes more universes. The making goes on. And now, in the closing, the phrase has its final meaning. We are inside something. The something is our home. It has been our home our entire lives. It has been the only home we have ever known. The night sky we have looked at since we were children. The galaxies we have read about. The stars we have watched. The moon. The sun. The clouds. The forests. The mountains. The oceans. The cities. The roads. The houses. The rooms. The chairs we sit in. The beds we sleep in. The people we love. The people we have lost. The lives we have lived. All of it inside. The inside has been complete. The inside has held everything. The inside has been more than enough. The picture we have been walking through tonight does not change any of this. It changes the frame. It changes the question of whether the inside has an outside. It changes the answer to the question of whether the universe is finite or infinite, whether there is a parent universe or not, whether black holes are doorways or endpoints. It changes some metaphysical things. It does not change the inside. The inside is what we have. The inside is where we live. The inside is where every meaningful thing in our lives has ever occurred. And the inside, regardless of whether it sits within a parent black hole or floats freely in an infinite cosmos, has been our entire experience. It has held everything we have ever needed. It will hold everything we have left. That, I think, is the gentle place to leave it. The question is no longer rhetorical. I said this at the beginning of the video. I am saying it now at the end. The phrase, then, was an opening claim. The phrase now is a closing observation. The question is no longer rhetorical because the question is being asked, in the open, with data on the table, by working scientists, with instruments that will decide. The question has a deadline. The deadline is within the next decade. We will know. Until we know, we are in the brief window. The window between the asking and the answering. The window where the question is real and the answer is on its way, but the answer has not arrived. The window we live in. I want to say one more thing about this window. The window is not, in the deeper sense, a window of ignorance. It is not the gap before the truth arrives. It is instead a window in which the question itself has a particular quality that it will not have later. After the answer comes, the question will be settled. It will become history. The future will inherit the answer the way we inherit the heliocentric solar system from Copernicus and the expanding universe from Hubble and the cosmic microwave background from Penzias and Wilson. The answer will be in the textbooks. The wondering will be over. We get to wonder. We get to ask. We get to sit with the question in its open state. We get to fall asleep tonight not knowing whether we are inside a black hole, with the question gently held in our minds, with the picture we have walked through tonight gently resting in our awareness. We get to be the people for whom the question is, right now, a real question, with a real answer that has not yet come. That is, in a deep way, a kind of grace. The grace of being present for an unsettled cosmology. The grace of being the people who get to ask without knowing. We have walked through a lot tonight. The JWST data, the Shamir count, the Pathria paper, the Schwarzschild coincidence, the Popławski bounce, the Afshordiman-Pur-Hassan horizon, the four anomalies, the horizon as boundary, the recursion, the telescopes, the timeline, the window. I do not expect you to remember all of it. I expect you, by now, to be drifting. So let me leave you with the smallest possible version, the version that fits in a single phrase. We are inside something. It is perhaps all we ever needed to know. The something has held us. The something has been our home. The something has the stars in it. The something has the people we love. The something contains, somewhere in its vast interior this moment, you, the listener, me, the voice, the slow descent into sleep that is about to take you. The something is what we have. The something is enough. Whether the something is inside a parent black hole, or inside a parent universe of some other kind, or alone in an infinite empty void, the something is, from where we sit, complete. We have not been able to see anything outside the something. We will not be able to in our lifetimes. The something is our world. The something is our cosmos. The something is, in the end, what we mean when we say the universe. The universe is the inside. The inside is enough. Tomorrow the telescopes will keep collecting data. The papers will keep being written. In 10 years, give or take, the answer will be in. Either way, the cosmology of 2035 will be different from the cosmology of 2026. The change is coming. But for now, tonight, the question is open. The question is gentle. The question, in its open state, is one of the most beautiful things in cosmology. The kind of question that, once it has been asked carefully, refuses to leave you. You will remember sitting with the 4 words, "We are inside something." You will remember the strange, quiet peace of accepting that, whatever the answer turns out to be, the inside has been your home, and the home has been enough. The video is ending. The night is winding down. The stars are still in the sky, wherever you are, whether you can see them or not. The Milky Way is still rotating around Sagittarius A, which is either the supermassive black hole at the centre of our galaxy, or the doorway into another universe, depending on which cosmology turns out to be right. The galaxies in the JWST JD's field are still rotating in whatever direction they have been rotating in for billions of years. The 263 of them that Shamir counted are still there, still spinning, still bending toward an axis we may or may not, in 20 years, have come to understand. We're inside something. It is enough. Good night.